Good afternoon, or good morning, or good evening, whenever you're watching this. My name is Adam Thompson, and I'm a Senior Solutions Architect at NVIDIA. Before I begin my presentation, I did want to extend a warm thank you to the SciPy organizers and the entire SciPy community. It's really amazing that we pivoted so quickly to this digital content for the conference, given the challenges that we face with COVID-19. And as much as I want to be with all of you all eating barbecue in Austin, Texas, I've never been, really was looking forward to it. I'm glad to still be here today to talk about GPU accelerated signal processing. Before I start, just a word on Rapids. If you're not familiar with Rapids, it's NVIDIA-led, but community-driven open GPU data science. So cuSignal, which this presentation concerns, is GPU accelerated signal processing, but it's one of many libraries in the entire tool. Also, I want to say that the entire Rapids team and myself stand for equality and social justice as we face these unique and specific challenges here in the United States. So again, I mentioned before that Rapids cuSignal is GPU accelerating SciPy Signal with Numba and CuPy. So a lot of this work comes down to this fundamental idea that we can take a beloved and super helpful library like SciPy Signal and quickly and easily GPU accelerate it using common tools and open source tools that are already provided in the community. So for this particular effort, we used both Numba and CuPy. So there's really two themes and two tracks of this talk. The first track is if you care about high performance, easy to build signal processing with Python, then, hopefully at the end of this talk, you'll say, wow, what, this library is promising and exciting. And I can get, build these workflows, quickly and easily. Further, if you don't care about signal processing, I understand some of you guys exist and some of you girls exist. This shows hopefully an effective way to build GPU accelerated data science libraries. So we go through the process of building Pythonic GPU accelerated libraries without ever touching CUDA or C or C++. My contact information is on this lead slide. And I'd also like to acknowledge the amazing contributions of the entire cuSignal team, including Matt Nicely, Graham Markall, and Brad Reese. So let's start with an example. Polyphase resampling has always been a compute-intensive task for signal processing workflows. If you're not familiar with polyphase resampling, essentially what you do is you get in a signal of a certain data rate and you want to change that rate, right? Potentially you're getting too many samples per second and you don't need that fidelity. Remember, a sample is basically taking a point in time of an amplitude of a signal, so to speak. There's tools like a regular resampler, but the polyphase resampler tends to keep the overall shape of the waveform, and it uses what's called a polyphase filter bank. If you look into the specific code within SciPy Signal, you'll see that it basically calls the upsample filter downsample or up for down routine. Furthermore, this up for down routine is written in Python C code. So the SciPy Signal implementation of this polyphase resampler is performant and it's quick. So what we're going to do here is step through some of the performance results of the polyphase resampler and go over our results here with cuSignal. So here's a snippet of the code, right? This is relatively straightforward. What we're doing here is we're creating 10 to the 7 samples. For all of our examples here, we're using 64-bit floats, so float 64. Performance will obviously increase as you reduce your numerical precision. And in this example, we're upsampling by 2 and downsampling by 3. So we're overall changing the rate by 2/3. We set up in the line that's setting up that lens space, we're essentially setting up a 10 to the 7, which is that 1E8 number of samples for a sinusoidal wave. And then we just call signal.resamplePoly. Again, this is all on CPU. And on my dual socket Xeon E5, this code executes in 2.36 seconds. The timing, again, for this example is just around that resample poly, code snippet down there. As we move to cuSignal, a couple of changes immediately pop out. We'll go into these changes more in depth, but you can immediately see that the code looks very similar. Instead of NumPy, we use CuPy, and instead of SciPy Signal, we use cuSignal. We set up the same number of samples with the same numerical precision. These are float 64s. And then we do a cuSignal.resamplePoly, again with the same 2/3 sample rate, also with the same Kaiser window. And in this example, timing just the resample poly with timeit, we go to 8.29 milliseconds. So this is 285 times the speedup of SciPy Signal with a very similar API. How similar of an API? The changes are highlighted in green. So again, here, instead of NumPy, you're using CuPy, and CuPy is GPU accelerated a NumPy library. We also have an option to pre-compile CUDA kernels. This eliminates the just-in-time compile overhead. We'll get into more information about what that is here later in the talk. And then, we use cuSignal instead of Signal. And the mean squared error between the results of cuSignal and SciPy Signal in this case is super small, right? So what we can see is 2 orders of magnitude speed improvement for the same results with minimal changes to the API. These were all benchmarked on a V100. And before I go into any more detail, some of you may say, I don't have a V100. cuSignal has been tested on a wide range of GPUs ranging from the Maxwell architecture to current architecture, and also the PCIe version of our GPUs to the Jetson version. So there are some great developers in the community who are using cuSignal and the Jetson Nanos, which are $100 little embedded GPUs to do software-defined radio operations, which is really cool. So this isn't just targeted towards large GPUs. It works for the small ones as well. So speed of light performance, that's Polyphase Resampler, but how does this perform for other types of functions? Again, this was all benchmarked with float 64 data type and 10 to the 7 sample signals on a V100. Why did I pick 10 to the 7 samples? This was, sort of in my experience, a relatively normal sample rate that could come in. And the methods that were benchmarked in this case was just sort of a random selection. I know sometimes people fall into the habit of looking at benchmarks and finding the best ones and showing those, but I really did want to try to give a good representation amongst the library and amongst common functions that people building signal processing pipelines are interested in. So we can see here, we are looking at FFT convolution, a standard correlation, a normal resample, the polyphase resample, the Welch, a power spectrum density estimation, creating a spectrogram, which obviously has applicability for speech signal processing and audio signal processing as well, and then a 2D convolution. And so you can see here, again, we're getting, 1, 2 to 3, almost 3 orders of magnitude speed up over these this 10 to the 7 sample signals. And again, your mileage may vary. A lot of this depends on what's your data size. A lot of this depends on what's your data type. And all of those other things that fall out of this. What type of GPU do you have? So you can learn more about cuSignal functionality and performance by looking at the notebooks on the GitHub repository. And you can run our examples yourself. So benchmarks are always fun and interesting to give and get, a lot of good engagement. But, even from my level, I never trust a benchmark unless I can run it myself, right? So I've tried to be as transparent as possible with these in particular. So what functionality does cuSignal have? This is a further selection of algorithms that we include. We essentially started with the SciPy Signal API and quickly tried to build out GPU support for all of the major functionality that particular library includes. So we have support for convolution, filtering and filtering design, waveform generation, wavelets, spectral analysis, and others to come. So as cuSignal develops and more people contribute and it gets more of an adoption, we can see both SciPy Signal specific functionality to increase, and we can also expand beyond that. We already have an acoustics package, which is looking into real and complex Kepstrom generation. And on the roadmap, we are looking into GPU accelerated signal readers. So these are things like handling SIG-MF or VITA49 or Midas Blue files, for example. Also support for features like polyphase resampling, polyphase channelization and beamforming, digital beamforming applications. So why does anyone care? Stepping back a little bit, why does anyone care about signal processing on GPUs? I think this is no surprise, particularly for this community, but signal processing tends to be the basis for a lot of the information extraction and retrieval that we care about. And as we look at more adoption of 5G technologies, of IoT connectivity, there's a need for faster signal processing tools. So these are things like fast filtering, faster FFTs, faster correlations, faster convolutions. How do we handle more data? How do we handle larger bandwidths? How do we handle higher sample rates to gain insight into communication systems and to deliver, performance that has never been seen before? And further, there's this idea of artificial intelligence techniques really haven't been deeply studied for signal processing tasks. So how do you train a neural network to learn an FFT, for example? How do you apply artificial intelligence and deep learning solutions to do spectrum sensing or signal identification, or better yet, spectrum collaboration or anomaly detection? So for example, the FCC has allocated all kinds of specific bandwidths and channels for specific communication devices. And if you are an entity using one of these allocated bands and you never use it, someone else should be able to use it while you don't. But then if you need that particular frequency to transmit at, then you would want the ability to kick everybody off and to move on. So artificial intelligence techniques can be really valuable here for redefining how we think of and approach building these communication systems. So another important enabler with cuSignal is, SciPy Signal is a phenomenal little library, but how do we enable more online signal processing? Software-defined radios typically transfer small samples from the A to D converter to the processor for fear of dropping packets. Like that's the cardinal sin for software-defined radio, right? You don't want to drop packets. And so if you're on a GPU, if you have a multitude of small copies and then compute on the GPU, this just kills your performance, right? You're bottlenecked by PCIe. You're not leveraging density or concurrency with your GPU compute, and it's just a bad thing. So cuSignal has enabled online signal processing by essentially wrapping Numba's exposure of shared memory. And so this is both mapped and addressed memory that's directly accessible by both the CPU and the GPU. So in the cuSignal context, we can create shared memory with this cuSignal.get shared mem function. And so you can see here in this code snippet that if you look at the GPU pointer, which is in the CUDA array interface, we can see that that is the same pointer as the CPU pointer in the array interface. And since we're talking about CUDA array interface, cuSignal is compatible with all libraries that support this interface. And so we can this allows for zero copy data movement between any library that supports the interface. So the applicability of me talking about artificial intelligence solutions prior to this is that we can zero copy data that's been pre-processed with cuSignal over to PyTorch to start training on this data and looking to see if we can develop deep learning solutions here. In terms of actual usage, we had worked with a company called DeepWave Digital that has an AirT hardware platform that includes a Jetson TX2 in addition to an FPGA for ultra low latency signal processing. And we were able to show that we could get real-time signal collection and polyphase resampling at 62.5 megasamples per second with cuSignal. So this is showing there's a little bit more work to be done here, but it is showing that online signal processing is successful with cuSignal. And moreover, and more exciting is that this is all in Python, right? So we didn't touch these low-level software libraries. And with the exception of using get shared mem, from cuSignal, with the exception of that, we didn't really think about memory, which is pretty powerful. cuSignal also supports a zero copy connection to PyTorch. As we mentioned before, cuSignal fully utilizes the CUDA array interface, which is a Numba specification specifying how in GPU memory data can be represented. And so if you have a library that supports the CUDA array interface, you can pass data around on GPU by just passing pointers. So you don't have a physical memory copy involved here. Again, in this example, we are going to use 10 to the 7 samples. These are float 64 as before. And we are going to create this shared memory space between GPU and CPU. And then we are going to fill that memory space with random samples generated on the GPU. You could just as easily do this on the CPU with NumPy. But nevertheless, we are doing the GPU here. We can look at this pointer and then move that data array over to PyTorch. So now we have a torch tensor. This is done with torch.asTensor and specifying our device as CUDA here. And if we look at both of these pointers, both within PyTorch and within the cuSignal CuPy context, we can see that we have the same address. So we have done a zero copy pass of this data from cuSignal to PyTorch. As an aside, you can also move this torch array back to the CuPy cuSignal context with a CuPy.asArray. The cuSignal technology stack is unique within the Rapids series of projects. We don't feature a Python layer. So we have no native C++ or CUDA within the library. Instead, our custom CUDA kernels are written with Numba and CuPy, dependent on the speed that we're looking for. But nevertheless, this is all .py files at the end of the day. So how did we build cuSignal? And this is where the second story emerges with cuSignal. And it's essentially, if you're not interested in the performance the performance results of cuSignal and building GPU accelerated signal processing pipelines within Python. This is essentially showing you that you can use this recipe, this crawl, walk, run recipe of building GPU accelerated applications for whatever problem set you care about. And it goes a little bit like this. First, we take a look at our code and we look at the libraries that we're using in our Python code and look for drop-in library replacements for the GPU. So if we have NumPy code, we can use CuPy. If we have pandas or scikit-learn or network X code, we can leverage Rapid's cuDF, cuML, or cuGraph. So this is really saying that instead of import NumPy as NP, you could say import CuPy as NP. Hit the go button on your code, and you should just get an order of magnitude or more acceleration for free. So the pros here are a trivial code change and, this free performance increase. The cons, obviously, you have a lack of control, and you could have a potentially suboptimal result if you're chaining together these GPU libraries together without really making use or understanding the way that memory is managed. So now that we have the drop-in GPU library replacement, there are certainly algorithms and functions within your code that don't have support within these libraries. So here we can leverage a custom Numba CUDA kernel. These Numba CUDA kernels are just-in-time compiled, and it's a way for us to quickly build and test these custom CUDA kernels with a very Pythonic API. So a lot of the GPU-specific work here is boilerplate code, and so we can copy and paste to quickly and easily build custom functionality. The cons is that we have this just-in-time compilation overhead, and a lot of times we noticed in our work that there is an excess register pressure on certain data types. If we need even more performance, we can do the optimal solution here. And this is matching native CUDA speeds by writing raw CUDA code. So this is actual C CUDA code, and wrapping it in a CuPy raw module. So this is essentially what, we're putting C code into Python so we can match the native CUDA C++ speed. We have no additional software layer, so we still have no Python to expose Python bindings in here. But we have the disadvantage of you're basically writing C, C++. There's limited debugging tools. And if you want to support a different data type, you actually have to create a specific kernel for that data type. So what does this look like? So these three cases exposed with some code. First of all, let's look at the drop-in replacements. This is the easiest. And probably, honestly, 60 to 70% of the cuSignal code base is something like this. On the left, we have SciPy Signal, which is, a lot of NumPy code. And on the right, there's cuSignal. So the green is what's changed, right? So there are a total of, 6-ish changes to the code base, something really trivial. We can teach basically anyone to make these changes. And just with this, we got a 230x speed up over SciPy Signal on CPU with the V100. Transitioning to a custom Numba CUDA kernel. So looking at Lomskargale, and I've never actually pronounced the Lomskargale, so I hope that's somewhat correct. On the left, we have the Python implementation. Some code has not been shown just for brevity's sake. And on the right, we have cuSignal. So this is saying that there isn't a Lomskargale function available in any of these drop-in GPU library replacements. So let's make our own. So again, what you see here is we are importing the CUDA module from Numba. We're doing the just-in-time CUDA decorator at the start of this kernel. And then we do some CUDA specific things. So, when launching CUDA kernels and executing and writing CUDA kernels, we have to specify threads and grids and how to move through this organization. And so that's essentially what we do here. So it's a very Pythonic way of expressing these CUDA kernels, and the launch is not shown here. So there would be additional code that you would need when you actually launch this CUDA kernel from Python, basically establishing the blocks and the grids and the grid. But here we see a 322 speed up over SciPy Signal. And as we transition to the custom CUDA kernel, you can see a lot of green on the right-hand side, but we're getting 386x speedup. So the speedup increases over even the CUDA Numba implementation of these raw kernels. But here you see a template. You also see a lot of C code, and then, native CUDA. So you see the block IDX, the block dim, and the thread IDX in there as well. But this is sort of speed of light performance for these GPU accelerated applications. What's the future direction? So a large part of our future direction with cuSignal is focusing on more performance. Much of this involves, let's take a look at our existing code base. Again, the code is 60 to 70%, NumPy to CuPy. So are there any places that we can look into this code to do more of the custom CUDA kernels and to make optimizations there? We're also partnering with the CuPy team and supporting things like C++ template functionality, experiment with loading precompiled cubin files into CuPy. So basically this means that our precompiled kernels can be installed with cuSignal rather than compiled with cuSignal. So you wouldn't have to do that, that cuSignal.precompile kernels like we saw in the resample poly use case. And then just expand functionality, which I talked earlier about in the briefing, to look at polyphase channelization, beamforming, and GPU accelerated signal readers. This talk would not have been possible if it weren't for the open GPU data science community and developers, particularly those contributing to CuPy and Numba. These are truly fantastic pieces of work. And then there are 4 companies and individuals who have been transformational and a huge help for cuSignal development and testing listed there as well. And to all contributors past and future to cuSignal, we'd like to extend our warmest regards, thanks, and acknowledgements. So how to get started? I mentioned all this stuff about cuSignal, and this is where we actually get down to the brass tacks, right? So listed at the hyperlink is the GitHub repository for cuSignal. It's free, it's open source. We welcome contributions, we welcome issues, we welcome compliments and, areas of improvement. And you can also get the code via an Anaconda install and Docker containers. And the Conda support for our most recent stable release 0.14 is located there as well. So with that ends my presentation. I hope you have a wonderful SciPy conference and experience. And thanks for taking the time to learn more about GPU accelerated signal processing. Thank you.